using STATA to conduct multiple linear regression. Let's take a look at the following example. A healthcare analyst within the cardiology unit of a hospital would like to examine the effects of average walk-in time after heart valve replacement surgery and patient satisfaction with hospital services on length of stay after having this type of surgery. Data were collected for 8 patients, and their average walk-in time per week after the surgery was recorded, along with how satisfied they were with hospital services. Higher scores for satisfaction indicates more satisfaction with services. In this example, one of the first steps in conducting regression analysis is to examine the associations between each independent variable and the outcome. In this spreadsheet, we see that we have 3 variables for these 8 patients. So we have average walk-in time, we have patient satisfaction with hospital services, and we have length of stay at hospital. We already know the length of stay at hospital is our dependent variable. Patient satisfaction with hospital services and average walk-in time are the independent or explanatory variables. Again, data were collected on 8 patients. And you can see here that the average walk-in time is for the entire week. So for instance, in 1 week, patient 1 walked on average 28 minutes and reported a value of 18 for satisfaction with hospital services. Again, the higher the scores for this variable indicate more satisfaction. So the first step is to determine if there is some kind of a linear association between each independent variable and the dependent variable. In the first plot, scatter plot here, we plot x1 against versus the dependent variable, and we notice that the association is negative. As average walk-in time increases, the length of stay decreases. This is something we noticed earlier too. Now, in regards to the patient satisfaction, we notice that as the values of x increase, in other words, higher scores for satisfaction are associated with an increased length of stay. This is a positive association. Now that we examine the associations between each independent variable and dependent variable, we can go ahead and conduct multiple linear regression analysis. And in STATA, you can use the command regress, just like in simple linear regression. And when you enter the command regress, right after regress, you enter the dependent variable. The dependent variable has to go first, which in this case is length of stay, and then you place the independent variables walk-in and satisfaction. You may place satisfaction first and then walk. The order of the independent variables in the model does not really matter. Again, what matters is that you enter the dependent variable first, because STATA assumes that the variable entered after the command regress is the dependent variable. So in the next notes here, in the next slides, we'll be interpreting the overall model, R-squared, as well as regression coefficients. So let's take a look at the findings. Let's start with the findings in the tables, which are highlighted in green. Again, we have the command line, regress, length of stay, walk-in satisfaction. And the first table that we see that lists the source, the variations such as model, residual, sum of squares, and so on, pertain to the overall significance of the model. Or if you like, examining the fit of the regression model. So the fit of the regression model can be assessed by using this ANOVA table, and we can say that the overall model is significant. As you can see, the F-test with 2 and 5 degrees of freedom is 92.3, which is a very high value. Remember, a high value of a test statistic will yield a very small p-value. And indeed, in this case, the p-value is small, much smaller than 0.05, which is the significance level. And therefore, we can say that overall, this is a good model, indicating that most likely the predictors in this model will be significant predictors of length of stay. Next, we look at the R-squared. The value of the R-squared is 0.9736. So this means that the model accounted for 97.36% of the variation in length of stay. We may choose here the adjusted R-squared because we have more than one independent variable in the model, and we know very well that the R-squared tends to be biased upwards, meaning that it goes up every time you add another independent variable in the model. So even if you use the adjusted R-squared, you can see here that about 96.3% of the variation in length of stay is explained by walk-in time and satisfaction. Next, we would like to interpret the regression coefficients. And these results are highlighted in red in this slide. So we see that the regression coefficient for walk-in is negative 0.09, and for satisfaction is 0.08. And this reflects what we found in the scatter plots, where the association between walk-in and length of stay was negative. So here we have a negative regression coefficient, and for satisfaction it was positive. So we have a positive regression coefficient. Now, in terms of interpreting these coefficients, one may say that for 1 minute increase in average weekly walking is significantly associated with an average length of stay decrease of 0.09 when patient satisfaction does not change, or when we control for patient satisfaction. So as you can see in this sentence here, we not only interpret the 0.09, basically the coefficient associated with walking, but also we're making a comment about the significance of this regression coefficient. We say is significantly associated. And we make this comment because when we look at the p-value, we notice that the p-value is 0.001, which is smaller than 0.05, and that indicates that this particular predictor is significant predictor of length of stay. Similarly, for patient satisfaction, you might say that 1 point increase in patient satisfaction is significantly associated with an average increase of 0.0824 days in length of stay when average weekly patient walk-in does not change, or controlling for walk-in. And indeed, for satisfaction, we notice that the p-value is 0.013, which indicates that this is also a significant predictor of walk-in, of length of stay. The following table shows the data associated with the predictor length of stay based on the regression equation that we computed from the previous analysis. So as you can see here, we may use the predicted equation of 13.1087 minus 0.090 associated with the slope of the first independent variable, plus 0.0825 associated with the slope of the second independent variable, and we can use this regression equation to compute the predicted values of y. So that way we can then compute the residuals, which is again the difference between the predicted and the observed values of the dependent variable.